Good morning, guys. So I hope you understood the class which we taken in the Saturday classes, right? The topic I hope you it's clear. In today's video, we'll be having combination of both the last portion of laws of motion and this initial or introduction or a little bit details in the from the chapter of the first chapter, which is work, energy, and power, which is the continuation of something which you have learned in the ninth class. Okay. So I hope you remember the last derivation which we did during the circular motion or the circular level road, right? We found maximum velocity is equal to a root of mu s rg, right? Right, this was the maximum possible velocity of any vehicle which is traveling on a level road. Level road means if this is the road section, the inner layer and the outer layer will be on the same level. That's why it is called level road, right? This is something which I have taken, right? Right, and mu(s) is the static friction between the object and the road. R is the radius of the road. And what do you mean by radius of the road? When you have two circles, right? When you're considering circular motion, you're having two circles. So what do you mean by radius? Radius is actually something which you take from the center of the road. Clear? Right? And g is acceleration due to gravity, but usually they will be given as it is the radius of the road as it is. So nothing has been mentioned regarding the taking the radius from the center of the road. I'm mentioning because that is what actually happens. Clear? Now today's topic which we are going to deal with is banking. Right, so I have taught or told a little bit about banking in the live class, but I'm repeating again. That is during or when you go for a long voyages in the hilly areas, you will see that when you construct a road, I'm drawing it again. If this is the road, it is found that the inner circle, right, is lower than the outer circle of the road, right? Let's say by an angle theta. That's what it is seen, or it is constructed in such a way, right? So in hilly areas, the outer circle of the road is raised when compared to the inner circle, and this process of raising the road is known as banking, and this theta is known as banking angle. Right, so if you are having a car, let's say like this, which is traveling on a banked road, right, so it will be having a centripetal force, right, let's say in this direction, which is equal to mv squared by r, right? This centripetal force is given by, actually remember I told a lot of examples regarding what and all the things which provide the centripetal force, and told you centripetal force is an imaginary force which is generated by different other forces, right? Just like our examples which I have taken in your live classes, right? Sometimes it will be the normal reactions component, or sometimes it will be in the case just like the level road, it will be just friction as it is, right? So it can be of different conditions. So what and all can be written then? mg, which is downwards, and then this will be normal reaction, right? This and all are something which you know. And there is a friction here, right? Let's write friction as just f. Clear? Right, this and all are the common thing we know. So I'm going to draw the what you say as our free body diagram. So this is the inclined plane, this is the block, right? So here what and all force will be there? One is mg, the other is normal reaction like this, simple, right? And this normal reaction, let's say this is angle theta, right? So let's say friction, this f will be in this direction, so this is f, right? So let's take this n is perpendicular to the surface of contact, but when you consider the vertical, right, so I can make n into two components actually, right? If this angle is theta, then this angle is also theta, right? If this angle is theta, see, now it is something confusing which you have to know. If this angle is theta, so what will be this angle? This is 90 degree, right? So I can say this will be 90 minus this will be 90 minus theta, right? If this one is 90 minus theta, then this angle will be theta. Just check by yourself, guys, I need not tell it, right? So this angle will be also theta, then this component will be n cos theta, and this component will be n sin theta. Clear? Right, now it is not completed. Similarly, force is also making theta angle here, so this or friction is f cos theta here, and this here will be f sine theta, which is the components of friction. Clear? Now write the equations for vertical as well as horizontal. In vertical, it is n cos theta is equal to what? F sine theta plus mg, as you see in the figure. It's the equilibrium condition. Now similarly, I told you here there is a centripetal force, right? And that means that centripetal force is given by who? Just look in the direction, right? Fc is equal to n sine theta plus f cos theta, right? Clear? And in place of Fc, I can directly actually write it as mv squared by r. But I could have written here now. I will write here mv squared by r. So you have two equations now. Right? Now, in the just like the previous cases, if the body is not supposed to move, then the static friction should be less than or equal to its maximum friction, which is limiting friction. And what is limiting friction? It is mu s into n. Right? Clear? So Fs should be less than or equal to mu s in the n. That is the maximum friction possible, static friction possible. So from the first equation, you can write in place of Fs, I will write, or in your F friction. This is actually your friction force, no? I write it as mu s into n. So first friction I am rewriting, or first equation I am rewriting as n cos theta minus mu s into n sine theta is equal to mg. Right? Similarly, this becomes your third equation. The next equation, the second equation, I'm going to write it as, right, n sine theta plus mu s n cos theta is equal to mv squared by r. This is your fourth equation. Right? Clear? Now, from the first equation, look into the first equation. Right? First equation, you can write, right, the same equation itself, right? I'm just rearranged it. So in the third equation, I'm going to do some adjustment so that I can write n cos theta. I can just write the n from there. I'm skipping a step, okay? N can be written as mg, right? This, or I can write it as mg minus mu s n sine theta divided by cos theta. No, it's better. No. Sorry, I'm going to change this one because it looks odd. Let's bring n terms common here. That's better. So n common. This is the third equation. Okay, cos theta minus mu sine theta is equal to mg, and from here I can write n is equal to mg divided by cos theta minus mu s sine theta. That is perfect. Now I'm going to substitute this n value in the fourth equation here, right? So that n sine theta now can be written as mg sine theta divided by cos theta minus mu s sine theta minus or plus mu s into n, that is mg divided by cos theta minus mu s sine theta, right? Simple, right? Mu s and then n, then there is a cos theta here, so that will be written over here, right? Is equal to mv squared by r. Right? Look at the denominator of these two sections, same now. So I can write mg sine theta plus mu s mg cos theta whole divided by cos theta minus mu s sine theta, that is equal to mv squared by r. Now this term is having m, this term is having m. I can cancel m here. Alright, clear? Or see, what I'm going to do is I'm going to divide the numerator and denominator with cos theta throughout. So this will be g sine theta by cos theta plus mu s cos theta by cos theta whole divided by cos theta by cos theta minus mu s sine theta by cos theta. That will be equal to V squared by R. Right? What is sine by cos? Tan. So it becomes G tan theta minus mu s. Cos theta cancels. 1 minus mu s tan theta. Right? This is equal to V squared by R. Right? Clear? Right. So, did I miss something? Right. We missed a G here. Right? I forgot. Sorry. Similarly, there is a G because we have to take common as G outside. Now, G tan theta minus mu s divided by 1 minus mu s tan theta. That is equal to V squared by R, or I can write V squared is equal to Rg into tan theta minus mu s divided by 1 minus mu s tan theta. Right? This is equal to, I can write V is equal to root of Rg tan theta minus mu s by 1 minus mu s tan theta. Now this is the expression for maximum velocity which is allowed in a banked road. The derivation you have to mug up as it is, and the final equation has to be mugged up. Right? So see, initially what was the equation for maximum velocity in the case of a normal level road? It is mu rg, or I can say mu s rg. Right? So here also there is mu s and there is rg. Just what I can say, angular section has been included. Clear? So when you say the road is smooth, right? When the road is smooth, mu s will be 0. There is no friction. Then maximum velocity in the case here becomes what? Root of Rg tan theta. Take it as a special case. Clear? This is the only theory which was pending from your laws of motion. You have to mug up the the derivation. I'm sorry I missed out the G inside or in between it. Was a carelessness from my side. Okay, clear? Now we'll move to the next new chapter, which is work, energy and power. Right? So let's write the heading as work, energy and power. I believe you guys have learned about it in your 9th class. A lot of them. So someone asks you, what is work? How would you explain it? You will say, I'm studying from morning to evening. I'm doing work. I'm sitting there itself and I'm reading. Right? I will say you guys are not doing work as per physics. Right? So the normal way of explaining work by a layman is quite different by a person who studied physics. If you are asked what is work, he will be giving a very different definition. Right? What is the definition? He would say, right, that work is the scalar product of force and displacement. That is what he would say. As a person who has studied physics, at least in the 11th class, he would say that force is the scalar product of force and displacement. Right? Clear? Work is a scalar product of force and displacement vector. Right? So work, I will write it as, this would be a dot. Scalar product means F dot S. Right? This is the equation for what? Work done. And F dot S, we can write it as magnitude of S into cos theta, with the theta as the angle between force and what? Displacement. Now, we'll start with the simple thing which you have learned in your 9th class. There is a block, let's say like this, M. You applied a force here so that it was changed its position from here to here by a displacement S. You would write work done is equal to F into S. Right? But see, the same can be changed here. Here there is a mass, there is a force applied with an angle theta. Right? And the block moved here by displacement S itself. So how would you say here work is done? Because work is not in this way, right? So you know work is actually equal to force into displacement, or I can say force in the direction of displacement, right, into displacement is work done. See, force in the direction of displacement, right? Force in the direction of displacement into displacement or dot product of them will give you work, right? That means, see, what is the force component in the same, in the directional displacement? It is this one, right? The same direction or in the same plane, I can say, right? This one. So this is F cos theta, right? This will be F sin theta, which will be equivalent to mg, and then there will be normal direction. There is no motion in the vertical direction, right? Horizontal direction motion is there, and that is caused by F cos theta. So that means here work is equal to F cos theta into S, right? So that is a cos theta product. That's why we write actually work is equal to F dot S. Clear? Better to study by this equation. Clear? Right? And what do you mean by, what do you, someone asks you what is a unit of force or unit of work? Work is equal to force into displacement, that is Newton into meter, or basic unit is joule, right? And what is the dimension formula of work? Force ml t raised to minus 2, displacement L, so dimension formula is ml squared t raised to minus 2, right? Now some of the cases you have to learn. First one, when the force and displacement, right, are in same direction. Same direction in the sense, if this is force, the displacement is also in this direction, which is commonly thing which you have learned. Here theta is equal to 0, there is no angle between them. Thus we can write F dot S, which is work done, right, will be Fs cos 0. And what is cos 0? 1. So when force and displacement are the same direction, I can write work is equal to Fs, right? Need not look into the other parameters, right? Whereas you would ask me the second condition, that is if the force and displacement are such a way that they are opposite to each other, or I can say this is force, this is displacement, that is they are making an angle of 180 degree with each other. Then in this case I will write Fw is equal to F dot S, that is Fs cos 180 degree. And what is cos 180 degree? Minus 1, or I can say negative Fs. That is, here now work is negative nature, here work is positive nature. Yeah. Now this one, then you would ask in which condition it is going to happen that you are applying force in the forward direction but the block is moving in opposite direction. Or I can say when which condition the force and displacement are in the opposite condition. This can be explained by using a numerical formula, so that it will be very much understood by you. Suppose there is a rough surface like this and there is a block here. We are applying a force, let's say 50 Newton, right? Let's say here the coefficient of static friction, or just say static friction is mu s is equal to 0.1 and mu k, let's say, is 0.2, right? You are asked what is the work done by the external force, which is 50 Newton, right, and frictional force. You are asked what is the work done by the external force and frictional force when this 10 kilogram block is displaced by a distance of 5 meter. Clear, right? So we are having, see, keep this in mind guys, different forces will generate different amount of work, right? So you will be particularly asked what is the value of this one, what is the work done by this force, etc. You commonly will be never asked, or even if asked, it will be what is the total work done. Clear? So we will start with the first section, that is work done by the external force, which is 50 Newton. Say in this figure itself I'm going to draw, let's say there is how much is the displacement told, it is said that is displaced by 5 meter. So after 5 meter, let's say the block has reached here, so this becomes 5 meter, right? So here I will write due to external force, what is the work done? Work done by external force is equal to force external into displacement dot, right? What is the angle between 50 Newton and 5 meter? 0 degree. So I can just write it as Fs, that is 50 into 5, that is 250 joules. Simple, right? Whereas in the next case, this is the second question, you are asked what is the work done by the friction. Now that is a different thing, right? See, you have to draw the friction section, and you don't know what type of friction it is going to be, whether there is motion it will be having or no motion, right? So we'll start with the first limiting friction, which is mu s into n, right? What is mu s? 0.1. And what is n? This will be n, this will be mg. Mg is 10g, right? N is equal to 10 into g, right? So I can write it 0.1 into 10 into 10 100, or I can write it as 10 Newton is the frictional force. Now motion is in this direction, so frictional force, the limiting friction is just 10 Newton, whereas in the forward it is 50 Newton. So will the object move or not? Yes, the object will be moving. So it is not the static friction which is going to act, but the kinetic friction, right? So what will be the work done will be done by kinetic friction, which is mu k into n. What is mu k? 0.2, right? N is 10g, right? That means you can write it as 20 Newton. So this block, forward 50 Newton, backward 20 Newton, right? So what will be the work done by the frictional force? Work done by frictional force is equal to force of friction into your dot product with what? Displacement, which is 5 meter, right? Now displacement is in this direction, whereas the friction is in this direction. So the angle between them is 180 degree. That means I will write minus Fk into what? 5 meter, right? That is minus 5. If Fk what it is 20, and what is 5k? So you will get minus 100 joule is the work done by friction. If the work done by the force is positive, the work done by the friction is negative in nature. That's why I can say the forward motion will be happening beautifully. Clear? Right. Now the third case which you have to learn, right, is when the force and the displacement are perpendicular to each other. That is, the angle theta is 90 degree. So you will write W is equal to Fs or F dot S, or I can write Fs cos 90, where cos 90 is 0. So I can write work is equal to 0. Right? That is, this is your block. Let's say, same example I'm taking, right? Let's say the friction mu s is 0.1 and mu k is 0.2 coefficient, right? And 50 Newton is applied here, the 5 meter displacement for the block to reach here, right? The same example I'm going to take, right? Here you are asked what is the work done by the gravity and normal, right? So we'll do that one. So this will be normal and this will be gravity, which is mg, right? So let's say what is the work done by normal. It will be normal force into or dot displacement, right? Now just look into the normal and displacement. This is the normal, right? And the displacement is in this direction. So what is the angle between them? 90 degree, right? So I can say that this dot product, if I am writing, it will be ns cos 90 degree, right? And what is cos 90 degree? 0. I can write work done by normal is 0. Clear? Now similarly we can go for gravity. Gravity's force is mg, right? So here, look here, this is mg and this is the displacement. Again the angle between them is 90. So the work done by the gravity is also 0, right? So work done by gravity is also 0, right? Now in the 9th class you would have learned about a coolie, right? That is, he's carrying a block or load on his head and you are saying that the person is doing any work. Now that is an utter nonsense, right? So 9th class you guys are not reached the actual level. That's why it is told no work is done, but work is done there, right? That is, if the coolie is carrying the load on his head, then the gravity is not working. So gravity is doing no work because he will be moving in this direction, gravity in this direction, angle will be 90. So the work done by the gravitational force is 0. But when he is going, right, this is a person, right, he is taking a load on his head and he going, means there will be a friction acting over here, right? That friction is in opposite direction as that of the displacement. That means there is a negative work done by what? Our friction. Total work done is not zero in the case of, that's why the person feels very tired when he is taking a load. One, there is a weight, right? But he is doing a work actually. But in your 10th class, you will be taught in a simpler way. That's a no, that's the way why you are taught there is no work. Actually, that person is doing a work against friction, right? That is, he is doing an against work, right? That is why you say friction is doing a negative work. Clear? Right? Clear? Now we move on to the sorry. I'll make the voice, I'll make it silent. Now let's move on, right? Suppose there is an inclined plane like this, right? And let's say there is a block M here, and automatically the block is coming from here to here. It is displaced like this, so that the displacement, let's say, is L, right? You are asked what is work done by the gravitational force. Let's say this is theta. Okay, work done by the gravitational force and normal reaction, sorry, right? So first we will start with normal reaction. Very simple. This is normal reaction, this is displacement, right? What is the angle between N and L? 90 degree, right? So normal reaction is not doing any work. This the first part is N and L 90 degree, right? Perpendicular. So work done by normal reaction is 0. Now we cannot say the same for gravity. Why? Let's draw. Okay, here itself, let's make this, I'm going to rub this off. Okay, right? So this, I told you, if this is the weight mg, this will be mg cos theta, and this will be mg sin theta, right? Remember, and the displacement here is L, right? So that means what is the force which is in the same direction as of the displacement, right? Actually, what is work? Work is equal to force in the same direction as that, or in the same plane as that, or along the displacement into displacement, right? Or dot product, right? Clear? This is the equation actually, dot product or scalar product of force in the same plane or the same line as that of the displacement or along the displacement, right? I'm not talking about the perpendicular condition, guys, right? This is the actual way of finding, right? So this one, mg sin theta, is the force actually which is causing this displacement, right? So I will write W is equal to mg sin theta into L, or dot L. Right? Now this mg sin theta and L are making 0 degree with each other. That's why I can write W is equal to mg sin theta L. Now this and all are not equation, guys. I'm doing problems here. Clear? Right? Now we'll move on to the next section. Guys, if you are not understanding, pause the video and try to do the problems by yourself. Right? Now there is another problem. See, I'm supposed to draw a sphere, hemisphere. I hope it looks like a hemisphere. Now this is the radius r, right? Then this also will be radius r. Okay, keep that in mind. Now here you are having a block, let's say like this, and the block, I could draw the block very small. Let's say this is the block here, and the block has been displaced from here to here, let's say by a force, let's say F, right? Right, so the block is displaced. Let's say this will be displacement, right? I will take another color, that's better. This will be displacement. That's how you take, right? Let's say this one, this angle is theta. This one, darkened angle, is theta, right? This much clear, right? You are asked some of the things. You are asked what is the work done here to by the force F to move from the bottom to the position by, if it is having a angular displacement of theta. This much clear. I'm going to remove this theta section, right? Clear? Right. So Now here is a very important criteria I'm going to take, guys. Keep that in mind, right? See, you know W is equal to Fs cos theta, right? Now, see, in this case, S is variable, right? Variable means S is not in this condition, not here like this. It is making actually an angle, right? I can say this is an angle, right? So that means here S is also having components and force obviously is having components, right? So what will can be having, right? So but you cannot say component for force. In the initial condition, what we did, we made force. When we found, suppose this was a flock, there was a force, we made two components, this became F cos theta, etc. We never made the displacement into components, right? So this is where I am going to take a very important section. That means, see, it is a dot product, right? And I told you A dot B will be equal to B dot A. Not in the case of cross product. Okay, A dot B is equal to B dot A. So if I write W is equal to F dot S, I can even write it as S dot F. No problem at all. Clear? Right? So that if it is W is equal to F S cos theta, it can be mean that F into component of S, or I can write it as S into F cos theta. That is a displacement into component of force. Both are correct. There is no problem if you write in that way. Clear? We just, in the slang, it is better to write Fs cos theta. This cos theta can be actually the S comes cos theta, or if the cos theta might be the component of force also, F cos theta. No problem at all. Right? Now let's move on to the problem. This is very important criteria, guys. That means I can write work, which we earlier wrote it as was force or component of force, right? Component of force along displacement into or sort of dot into or multiplied by displacement. That is what we earlier written, that is F cos theta. That is component of F along S is F cos theta into S. That's how we learned. Now we can even write work as what? Force into, just force into component of displacement, right, along force. Both are correct. That's what I meant. Clear? Now let's move on to the problem, guys. I'm going to redraw the problem. Oh, the sphere doesn't look good. Let's say this is radius. The block is so small that let's say this is also radius, right? The entire thing from here to here, right? Now let's say the block is here. This angle is theta, right? Clear? Now this will be the displacement, right? So what and all are the components of displacement? One will be in this direction, right, which will be same as this one. Keep this in mind. I will take another color that's better. See, displacement has two components, right? This same length will be here, right? Clear? So this x, if I am taking, is the component of displacement, right? And I told this is the direction of forces also given in this direction. So this x is the component of displacement in the same direction as that of F. Keep that in mind. Now, I'm going to remove this and all, right? I'm going to write this one only, this one, right? So what can be, this R is also a vector, right? Clear? Right? If this is radius, this is also radius, so to the surface, so this is also radius, right? So this is an angle theta, so this will be R cos theta, right? Then this will be R sin theta, right? R squared sin cos squared theta plus R squared sin squared theta, you will get R, right? So if you are considering this triangle like this is R, this will be R cos theta, and this will be R sin theta. And we just wrote this as x, right, before, and I told you this is the component of S. Even if, see, component of S, magnitude, right, this was a component of S, right, and I told you this length and this length are same, right? So I can write x as what? R sin theta. So work done, forces having no component F, into component of displacement is x, right? And the magnitude of x as per the figure is f into r sine theta, right? Clear? This is your work in this problem. Clear? Simple. Now similarly, let's draw a pulley. I like pulley questions, don't know why, right? This is T, right? Let's say this is 2, this is 1 kilogram. The tension here 1g, here 2g, right? There will be tension here also, no? Same tension. This will be accelerated up, this will be accelerated down, right? Now you are asked what is the work done by the gravity and force on each mass and tension force, right? Has to be also right for it. So you are first we'll draw by, I will tell you each and force we are finding. I will tell you first we are going to find, let's stop using red color. Let's say first one we are going to find what is the work done by the gravity, right? Work done by the gravity by the first 1 kilogram. Let's talk with a 1 kilogram, right? How much is the work done by 1 kilogram? This one. How much? Force. What is the force here? 1, right? And we see guys in which direction the displacement is coming. This one is displacement downward, means this is displaced upward now. So downward force, upward displacement, angle between them 180 degrees. So the work will be negative minus 4fs, minus f is 1g, na? So 1g I will write it as 1 into 10, that is 10 into s, displacement I didn't tell, na? Let's say displaced by 3 meter, right? So it will be minus 30 Newton. Let's say the entire scenario is displaced by 3 meter. Clear? This much is easy, right? Now similarly work done by gravity in the case of 2 kilogram. This one work is done by 2 gram or 2g, 2 gram or 2 into g, that is 20 Newton downwards. And the displacement is also in downward direction, so angle between them is 0, so the work done is positive, that is fs, right? So I will write it 2g into s is 3, that is 20 into 3, that is 60 Newton, right? Clear? So the work done by or gravity on 1 kilogram and work done by gravity on 2 kilogram is different. Clear? Question, sorry, I'm extremely sorry. Okay, here in the same question you are asked what is the tension, right? Tension, what is the tension? You are asked what is the work done by tension force, right? So let's remove the red color, right? So we'll take, you have to find the tension, right? So proper way, what is this? 2, this is tension, acceleration downwards, this is 2g. So you will write 2g minus t is equal to 2a, right? In the case of 1g, t accelerated upwards, you will write t minus 1g is equal to 1a, right? Then you can solve these two equations. You can add these, so it becomes g is equal to 3a, or I can write a is equal to g by 3. Right? And you can substitute in any of the values here, right? You will get t is equal to 4 by 3g, right? Or see, there is a trick, I have told you the trick, or you can write the basic equation, trick equations, which is present in your SM. This is 2m1 m2 divided by m1 plus m2, this into g, right? Then also you will get the same values of the tension as 4 by 3g. See, but I won't prefer that you mug up the equations, right? Why? Even if it reduces the time, guys, you have plenty of equations. Later on system of particles comes up, lot of equations to by heart, you will not be able to by heart those equations, right? Or of course you have to by heart, so I don't think the extra luggage is better, right? This is something you can find by the logic, right? So we'll do the work done by what? Tension will do it, right? So let's say work done by tension on 1 kilogram, work done by tension in 1 kilogram, that is equal to force into displacement. Here the force will be tension, which is 4g by 3, and what is the displacement? 3 meter, so it will be 40g, right? So because here the acceleration is upward direction, right? Clear? And the displacement I can say is in the same direction as that of the tension, right? Tension is upward, displacement is also upward direction. Whereas the work done by the tension in the case of 2 kilogram, right? The tension into displacement itself, but here the displacement is in downward direction, the tension is in upward direction, so the angle becomes negative, hence, or 180, or I can say it is a negative work done, so it will be minus 40J. Why did I write it as minus 40? 4G by 3 is the tension, displacement is 3, right? So what is the net tension, guys? 40 plus minus 40, so it will be 0. That is, in the case here, net work done by the tension is equal to 0, but the net work done by, see, what is the net work done by our gravity? It is not equal to 0, right? So there can be many scenarios where the net work done by tension can be 0, but net work done by gravity is not 0, even if they look equivalent, right? Now note some points which I am going to tell you. That is, first condition, let's say F dot S, right? When we are going to talk about dot product of force and displacement, when theta is less than 90, that is, you are having an acute angle between force and displacement. That is like this. This is force, let's say this is displacement, and this is theta. This theta is less than 90 degree. If less than 90 degree means F dot S can be written as Fs cos theta, right? Here cos theta will be positive. When theta is less than 90 degree, cos theta is positive. So I can write work is positive, right? Now what do you mean by work is positive? That is, if work done is positive, right? That is, if you are doing, or when you pull, let's say when you are pulling an object, right, the object will come along with you, right? That is, I can say the speed is increased, right? When the speed is increased, means energy has increased, right? So when I say we have done a positive work on body, means energy of the body has increased. Remember, it is a very important criteria when you are working, right? When you are doing a positive work, right, then you are saying that the energy has increased in your body, or inside that body, right? Now guys, there is a okay, from the previous chapter there is a question which I want to do you guys to do it. Why is which is better, pushing or pulling? Which is easier, right? Find its answer, or do it as homework and send me personally. Let me see how many of you guys are able to do it. This is a topic or question from laws of motion, right? Which is easy, pushing or pulling in the case of inclined plane or any plane? Can take anyone, right? This is a question that just came up in my mind. Now let's move on with the work energy power. Suppose if the theta is greater than 90 degree, right? Right, if theta is greater than 80 degree, means that is, if the displacement is in this direction, that means force has happened in this direction. This is obtuse angle, right? So that means when it is greater than 90 degree, work is negative, because cos 90 degree will be negative, more than 90 degree will be negative values. Clear? So I like that. If it is in this way, that means work is negative, means if you are pulling the object in this direction, the displacement will be in the another direction. That means speed decreases, that means energy decrease. So if you are told that you are doing a negative work on a substance, means you are taking energy from that body, right? Or the body is losing energy, right? If you are doing work positive, the body is gaining energy. It is a very important criteria. Keep that in mind. Clear? Now we'll do some problems. Suppose you are given, this is in vector, force is given as 2I plus 3J minus 4K, and if this force is acting on a body, then the body is displaced from a point, let's say 2, 1, 0 to a point 3, 4, 2, and your work, or asked how much is the work done by this external force. How would you write? This is a vectorial representation. So this is actually R1 vector and this is position, or R2 vector, right? So I will write R1 vector as 2I plus J, and there is no K terms. Whereas R2, 3I plus 4J plus 2K. Put the caps, right? This is the vector representation and there is a vector here now. right? So your actually work equation is force into actually displacement, right? Displacement. So that means you are supposed to actually write it in the vector form. If you are writing it as work into F vector dot delta r vector, right? That is the displacement here. So delta r will be r2 minus r1. So delta r vector is equal to 3 minus 2 is I, 4 minus 1 is 3j, and there is no k, so it will write it as 2k cap, right? This is delta r vector. And what is force vector is also given. Now work, very easy question, right, is equal to 2y plus 3j minus 4k dot I cap plus 3j cap plus 2k cap. Now how would you do the dot product? Just multiply the items. 2 into 1 is 2 plus 3 into 3 is 9 minus 8. You will get the answer as 3 joules. 9 minus 8 is 1. 1 plus 2 is 3. Clear? So this much is the work done by the force. Clear? Right? Right. Now if two forces, right? If two forces F1 is given as 2y, 2y plus 4k, and F2 is given as 3j plus 2k. I'm not writing cap, okay? It is acting on a body, right? So that the body is displaced from 1 0 0 to 2 1 1. Please do the numerical by yourself by pausing the video, right? After doing that, then come, right? So what would be the net force? 2i. Is there any I term here? No. So it is 2i cap plus 3j cap plus 6k cap. That is the net force. What will be the displacement or vector? It will be 2 minus 1, that is 1i. See, I am doing it in the single step itself. You can write it as 1i plus 0j plus 0k, then you can write 2i plus 1j plus 1k, and then you can minus, but I am straight away doing it. So 2 minus 1 is 1i cap, 1 minus 0 is plus 1j cap, and 1 minus 0 is plus 1k cap, right? This is delta r vector, and you have force, net force vector also, right? You have to just find the dot product. That work is equal to F net vector dot delta r vector. So multiply items. 2 into 1 is 1 plus 3 into 1 is 3, 6 into 1 is 6. That is, you will get what? It is 10 joules, right? I believe it is 10. It is 2 now, so it is 11 joules. Sorry, 11 joules. Clear? Right? Now there is another section which is very, very important, guys, which is variable force. Now till here what we were learning is a constant force, guys, right? Now not in the direction case, that magnitude, see 30 Newton is applied in this direction, etc., right? So now we are going to consider if the forces are variable. That is, in a sense, if you are told that there is a force acting F is equal to 2x, you are asked what is the work when the body is displaced from x is equal to 1 to x is equal to 3. How would you do it? You will think, I will put 1 here, so it becomes 2. Then I will put x into 3, that becomes 6. Then I will do what? You get F1 and F2, right? Then you will 2 into 1. No, that is not the method, right? Because it's a different phrase, right? Right, you cannot use this F dot S here, because F dot S or work done is equal to F dot S is used when F is constant. So when F is not constant, that means F is variable, the method which have to be introduced is called integration, right? You have to use integration method, about which we have, I think, no, you have an idea? I don't think you have an idea. I don't know if you have taken. See, differentiation means you are having a bigger section, you are making it a smaller components, right? That is differentiation. Integration means you will be taken a small section, you will add a multiple of them to get a bigger quantity. That is integration, right? I will tell you with an example. I believe I have taken. Why do I feel that I have taken it? Right, suppose For this we are not doing that. We will do that question. Before that, something I have been taught. Let's say this is force and this x is the displacement, and we are showing the case, right? What is the relationship between force and displacement of an object, right? Let's say initial position is x1 and the final position has reached to x2, right? This much clear, right? And see, this much is equal, see, right? So you can say the force is not constant. Let's say here F1, then there is another force here, right? So the force is changing in this condition for that body, right? So you can say there is a variable force acting on that body, right? Right. Now we consider a strip, right? For this we will now, to solve this type of question, what would you do? We'll consider a small strip like this. Let's say the thickness or the breadth of that strip is dx, and the length of that strip is, let's say, is f, right? So how would you find the area of the strip? The area of the strip will be equal to length into breadth, that is f into dx, right? Clear? That means what is force? This is force into displacement, sir, right? This is in the displacement section. So I can write this area of the strip gives you a very small amount of work, that is dw. So dw is equal to f dot dx, right? The area of the strip gives you this much area, which you are seeing is f dot dx, right? And this is work done, right? Similarly, if I consider multiple of strips like this, right? Clear? So for this the f1 will be different. Let's say the thickness are all same, dx itself, right? So how can I see this multiple strips, when they add, they form the entire area, right? So the total area, if you are writing total area, I can write it as what? f1 into dx plus f2 into dx plus f3 into dx, and goes on. And this multiple strips, when they are added, you get the total area, right? Now what does the, see, total area, so each area is f dot dx. What is w1? Let's say it as dw1, small na, dw1 plus dw2 plus dw3, and goes on, right? So I can say this total area is actually total work. Hey, total work is equal to small works. When you are add, you get the total works, right? This is a tedious process. That's why we are going to introduce the section called integration. That is how I am going to write total area is equal to integral, right? F dot dx, f dx is multiplied. So I will write common as f dx, and the limit is from x1 to x2, right? This much strip, one is f dx. Similarly, there is another dx, f dx. Similarly, at that much amount of f dx, I am going to add from which limit? From x1 to x2, sir. And what is this total area? That is our total work done. So total work done in the case of a variable force is x1 to x2 f dx. Work done by a variable force expression is given by Wt is equal to integral x1 to x2 f dx. Clear? Very important, right? So from this derivation, right, in between the steps, what and all we have noted? We have first noted that we draw like this, dw is equal to f dx, right? And we wrote in this equation Wt into integral of f dx, right? That is, if I have a force displacement graph, the area under force displacement graphs gives you work. Keep this in mind. The first point which you can learn from this equation, or this entire thing which we have learned, is area under a force x graph or a force displacement graph gives you work done, right? And the second case is, if you integrate for a variable force, if you are grinding, the variable force generating a work is equal to integral x1 to x2 f dot dx. These are the two important criteria which you have learned from this derivation. Clear? Right? Right. So we will do small problems to make this section very comfortable. Let's say there is a force section here, and there is a displacement axis here. Here there is 5, right? This is 10, this is 10, this is 5, right? right? And you are asked what is the work done here. This is a very simple question. So I told you work done can be got from area under what? F displacement graph. Right, so what is your area? Here are two sections, one is rectangle and the other is triangle. So rectangle I can write it as what? 10 into 5, right? This is the area, plus then it is triangle, half into base is 5 to 10, right, into height is 10, right? So you will get 50 plus this is what? 2, right? I hope this is correct. Calculation you guys can do anyways. So it is 5, right? 25. So you will get what? 75 joule as the work done. Clear? 75 joule. Why it is right 76 here? I meant 75, but I don't know. Right? Clear? Now the question, we introduce this variable or variable force by starting with the question, right? F is equal to 2x, right? So we had stopped here and I told you we have some calculation pending, right? And we were told that the force of is equal to 2x and the work done is asked when the displacement is from x1 1 meter to 3 meter. How would you do it? You know, work is equal to what? X1 to x2. It's a variable now, f dx, right? So you will write x1 to x2, right? This is x1 one much is 1 meter, x2 is 3 meter, f dx, in place of f I will write 2x, then dx, right? Clear? That is equal to 2 is common, 1 to 3 x dx, right? What is integral x raised to n dx? If you don't know, write it as x raised to n plus 1 divided by n plus 1. There is a plus c but need not write here, right? So integral x raised to n dx is x raised to n plus 1 divided by n plus 1. Here x raised to 1, right? So I will write 2, x raised to 1 plus 1 is 2 divided by 1 plus 1 is 2. So upper limit, lower limit, right? After integration, remember this limit has to be put here in x. Upper limit minus lower limit, 2. Now this 2 cancels off, happy, right? So this 2 cancels off. So you can just write x squared upper limit, lower limit. Put value of 3 first, that is 3 squared, minus then put for lower value 1 squared. So 9 minus 1, that is 8 joule is the work done here. Clear? Right? Help, right? Now suppose there's a different question, guys. If the force is given in vector form, that is x squared, x squared I cap plus 2y j cap, right? And you are given the displacement is from 1, 2 to 3, 4, right? And again you are asked what is work done. So we cannot find here dx, right? See, we cannot write it as f dot dxy because here y component is also there, x component is also there, because there is a vector form here. So there is a twist. Here, when your force is given in a vector form as well as in a variable form, then the equation becomes R1 to R2, where R1 is having both x and y1, right? F dot dr. Keep this in mind. Variable force in vector form can be solved by this method only, right? W is equal to, total work done is equal to integral R1 to R2 F dot dr. Keep that in mind. Right, so r vector, right, is equal to, if it is given as xi plus yj plus zk, so that means dr vector will be dxi plus dyj plus dzk, because small r means tall x, small y, small z, right? Clear? Right, so here w integral r1 to r2 vector, I will write it as fx, right? So it will be x squared I cap plus 2y j cap, right? Dot dx, dr vector na, dx I cap plus dy j cap plus dz k cap, right? Now what would you do? You are having a dot product, right? So multiply the dots, that is r1 to r2, x squared into dx, right? Then there is only j, so I can write it as r1 to r2 then you can write 2y into dy. Right now guys, it is better, this component is having x only, this component only having y. So in place of r1 and r2, I can actually write it as what, x1 to x2, right? X square dx plus y1 to y2, 2y dy. Why? Y components only, so you are finding the variation from y upper limit to y lower limit. You are finding variation from x upper limit to, sorry, lower limit to x upper limit. This is the way. All the points, remember what is like our x1, x1, okay, 1 and 2, and there is 3 and 4, right? So this is your x1, y1, this is x2, y2. So 1 x displacement is from 1 to 3, x squared dx, plus y's displacement is from 2 to 4, 2 to 4, 2y dy. Now calculation you guys can do. So x squared dx, x raised to 3 by 3, 3, 1, x raised to n plus 1 I did. So 2 into y squared by 2, so 2 goes off, so y squared 4, 2, right? Then just substitute the upper limit and lower limit, right? You will get around 62 by 3 joules. Clear? It's not that tough, just do the calculation. x cube means this becomes 27, right? 27 by 3 minus 27, right? That is 1 by 3, 27 minus 1, right? Yeah, so it will be around 26 by 3 plus 12, 16, that 4 squared minus 2 squared. Clear? That's not tough. I hope this much is clear, guys.